Lab number 5 is entitled DJ Mixer, Audio Spectrum Filters for a Color Organ. A color organ is a system which causes a set of lights to change dramatically with music tones and levels. It usually consists of 4 active filters which divide the audio spectrum into distinct colored bands. Each band triggers a set of lights, which in our case will be LEDs that are red, yellow, green, and blue. In a commercial design, these are usually floodlights. So in this lab, we're going to design the active filters for the color organ, and then in a later lab, we're going to add comparators and the LEDs. Suppose we divide the audio spectrum into 4 regions: sub-bass, which would be tones below 100 Hz, mid-bass, which are tones between 100 Hz and 500 Hz, mid-range, which are tones between 500 and 2K, and treble, which are tones above 2 kHz. This is shown on the next page. We have our audio signal coming in, and then we're going to pass it through one of 4 active filters, which will let bands of frequencies through. For the treble case, we're going to let everything above 2 kHz. For mid-range, between 500 and 2 kHz. For mid-bass, between 100 and 500. And then for sub-bass, below 100. We can generally make the gain equal to 1 because we've got gain in other parts of our DJ mixer. I'm going to pick the values of Q for these filters. I don't want the filters to be too sharp, so maybe for the high pass and the low pass we could just use a Q maybe around 0.707. This would be the Butterworth second order constraint. For the bandpass filters, we know the 3 dB frequencies that we're going to set. Center frequency is actually the square root of their product. You can find this in the 202 ebook in chapter 12, page 37. Now the value of Q is the center frequency divided by the 3 dB bandwidth. So since we know the center frequency now and the 3 dB bandwidth, we can solve for the value of Q. Thus we can solve mid-band bass bandpass filters F0. Turns out it's 224 Hz and the Q is 0.56. The mid-range bass filter has a center frequency of 1 kHz, again using the square root of the product of the two 3 dB frequencies, and the resulting Q of 0.67. Before you come to lab, I'd like you to meet with your lab partner and design the active filters using the infinite gain multiple feedback circuits that we talked about in chapter 2 on pages 42 to 46, and also in supplemental 2.9 and 211. Design procedures were developed in these pages in supplemental problems, but because of the specifications I've just set up, you may have to redo the design procedure if you wind up getting negative resistors in the calculations. Again, limit your selection to resistors between 1 kilo-ohm and 1 mega-ohm. Prefer again not to use any series or parallel combinations. This isn't real serious setting of frequency, but I'm going to cover this audio range in 4 distinct groups. Do a piece-by simulation of your combined design, and please read over the lab procedure before coming to lab because there will be a quiz. Make 2 copies of your design and submit one to your instructor, and then hang on to that other one so you can use it for the class and the constructions of the filters. Also bring your PSpice files so that you can put in the actual values as you're measuring the resistors and capacitors. This is Lab 5, Audio Spectrum Filters for a Color Organ.